Hello guys, welcome. In this video, I'm going to take you guys through the differences between gas chromatography, which is GC, and high performance liquid chromatography, which is HPLC. So I'm going to go through a number of points, right? And then I'm going to explain those points as we go further. So first and foremost, GC is a very good separation technique. However, as good as it is, it has a low application range. GC has got a low application range. This is because the compounds that are analyzed by GC should be volatile compounds. It can analyze volatile compounds, compounds that can easily be vaporized. And also the compounds that are analyzed by GC, they should be stable at high temperatures. Okay, so as you guys would recall that in GC we use extremely high temperatures. So our compounds should not be degraded as they are exposed to high temperatures. When we're using PDMS, the maximum allowable operating temperature was extremely high. So now we want our compounds to not be destroyed. So they should be stable at high temperatures. In other words, they should have thermal stability. So as a result of this, most organic compounds are analyzed by HPLC. So now HPLC has got a high or an extremely increased application range. Okay, so take note that HPLC can analyze a higher range of compounds compared to GC. Secondly, GC has a gaseous mobile phase, or we call it the carrier gas. So we might use the inert gas, helium, can use hydrogen, we can use nitrogen. Okay, so in this case, the most important thing to note is that this carrier gas will have no interaction with the analyte. The selectivity in gas chromatography has got nothing to do with the mobile phase, as it will have no interaction with the analyte. And then of the three, the one that is preferred is hydrogen, because as you guys would recall from Gollay's findings, hydrogen has got, if this is plate height, and then being the linear velocity. So hydrogen has got, this over here is the optimal velocity. This is H min, and then this is U opt. So hydrogen has got the highest optimal velocity. So as you would take note, the optimal velocity is related to the diffusion coefficient divided by the column radius over here. So nitrogen is large in this case, so it will have slow diffusion coefficient, and hence it's going to be followed by helium and lastly hydrogen. So since hydrogen is the smallest of the three, it's going to have a high optimal velocity in this case. On the other hand, in HPLC, we use a liquid a liquid mobile phase. In contrary to GC, the mobile phase in liquid chromatography will have some interactions with the analyte. You know, in GC, the carrier gas will not interact with the analyte or will not interact with the sample that has been injected. But in HPLC, there will be some interactions between the mobile phase and the analyte. In other words, the analyte is going to dissolve on the liquid. So now, due to these differences, guys, due to this gaseous mobile phase and liquid mobile phase, this will have a major impact actually on the HPLC column, on how we design the HPLC column. Okay, cool. Let's go further. We said in GC we've got a gaseous mobile phase, and as a result of that, in GC we're going to have lower viscosity, right, and lower density. We've got a gaseous mobile phase. In GC, we're going to have lower viscosity and lower density. However, in HPLC, we are going to have higher viscosity and higher density. Now, these viscosities and densities which differ between the two separation techniques will have an impact right now on the manner in which the column is operated. Because of a high viscous and high dense mobile phase, in this case, we are going to operate HPLC at high pressures. Remember, in GC, we've got low viscosity and low density of the gaseous mobile phase. In HPLC, we've got high viscosity and high density of this liquid mobile phase. And as a result of that, the pressures that we're going to operate our column for HPLC is going to be higher compared to the pressures that are used in GC in this case. Okay, another thing I can mention, which is quite important, because in GC we are using gaseous mobile phase, right? There is going to be a fast diffusion. There is going to be a fast diffusion coefficient, right? Because these molecules are in a gaseous mobile phase compared to HPLC. In HPLC, the diffusion in a liquid mobile phase is going to be slower. In this case, we're going to have slower diffusion coefficient in this case. As a result of this, what are we going to have? The reduction of the diffusion coefficient in HPLC column is going to result in slower mass transfer. Right? As you guys would recall, the Van Diemter equation, which is H is equals to A over here, which is the eddy diffusion, plus this term, the longitudinal diffusion, plus this C. So this C refers to the resistance to mass transfer. So basically, we've got a liquid mobile phase, and this liquid mobile phase will have slower diffusion coefficient compared to a gaseous mobile phase. As a result of the reduced diffusion coefficient in HPLC, this means that there's going to be a slower mass transfer in this case, which is related to the Van Diemter equation. Okay, let's go further. So based on this info, guys, it would be improper now to have, or impractical rather, to have the same column formats for GC and HPLC. Hence, in GC, we have got open tubular columns. Right? In HPLC, we have got packed columns. So what does this mean? Let's start with GC. So in GC, the open tubular columns, these are the long and narrow columns. So in other words, we've got high L, right? And then it's going to be narrow as far as the internal diameter is concerned. So now, these columns, we can gain efficiency and speed on open tubular columns. We can gain efficiency and speed in open tubular columns by reducing internal diameter. So if we reduce the internal diameter of the column, we're going to gain in efficiency. Take note that Gollay's findings led us to H mean equaling DC over here. So this is related to the column radius in the sense that U opt is related to the diffusion coefficient over RC. So if we reduce this parameter over here, we are going to have, we're going to increase optimal velocity, and hence speed of separation is increasing in this case by reducing internal diameter. Hence, we're going to gain on speed. As far as efficiency is concerned, efficiency is N which is equals to L over H. So now our H is going to be DC. So if DC is being reduced, we increase in the theoretical number of plates, which is efficiency. Do you see that? So basically, for open tubular columns, we gain in efficiency and speed by reducing the internal diameter. Right? So, moreover, if we reduce the internal diameter, right? If we reduce the internal diameter, we are also going to reduce the diffusion distances that would be covered by the analyte. So the reduction in internal diameter will also result into the reduction in the diffusion distances that would actually be covered by the analyte from the column center to the stationary phase at the wall. Right? So these are open tubular columns. For HPLC, we use packed columns. Now, packed columns reducing internal diameter does not necessarily have an effect on efficiency, right? So now, this column, it is packed with small particles. It is packed with small particles, and they are packed close together. So remember, I said an open tubular column is a long and narrow column. But now, a packed column, we are speaking of a short and wide column. Okay, maybe I was supposed to give maybe some dimensions here. So the length here might be 25 meters. Internal diameter 0.25 millimeters, right? Then over here, the length might be 25 centimeters, the internal diameter being 4.6 millimeters in this case. So can you see that this is a short and wide column? So it has got some particles inside in this case. So it's basically a packed column. So as a result of this being a packed column, the diffusion distances, of the analyte, what are these? These are actually the distances between these small particles. This refers to the distances between these small particles, right? And hence, the particles gives good efficiency, or the particle size gives good efficiency. So in this case, efficiency is still the same, L over H, as we are going to find out that H is related to 2 times dP, where this is the particle size. So if we are using small particle size, we are going to gain in efficiency, right? In HPLC. Take note that these columns are packed. We are using packed columns in this case. Okay, guys. So now let me just give you an example of what we are referring to when we're speaking about a GC column. In terms of length times the internal diameter times the film thickness, we are speaking of 25 meters, 0.25 millimeters, 0.25 micrometers in this case. Okay, so, and we said this is the long and narrow column, right? So we might be given this 25 meters times 0.25 millimeters by 0.25 micrometers PDMS column. So for your information, PDMS is the stationary phase. It is actually an apolar stationary phase whose major separation mechanism is boiling point. Okay, so versus now HPLC. For HPLC, you might be given a situation of 25 centimeters by, say, 4.6 millimeters. And then you might be told that this is, let's say, 5 micrometers. Perhaps you're told C18 here. So in this case, this is the length right? This is the internal diameter, and this here is the particle size, you know? Okay, so now I want us to look at something here, guys. I want us to consider efficiency. Take note, I want us to consider the overall efficiency between HPLC and GC. The overall efficiency. Now, efficiency is L over H. Okay, cool. So efficiency now, when we are speaking about GC, it's going to be L all over DC. In HPLC, it's going to be L all over what? 2 times dP. So I want us to look at this, guys. That L here, if it's 25 meters versus L here, which is 25 centimeters, which of the two, GC or HPLC, will have an overall high efficiency? It's definitely gas chromatography, right? Because of the length in this case. So GC has got a long length compared to HPLC, because 25 there, it's going to be 25 times 10 to the minus 2 meters versus 25 meters. So because of this length, right, GC is going to have an overall high efficiency, you know. And I forgot to mention that this C18 is going to be the compound that coats the surface of the stationary phase in HPLC. As you guys might take note, for HPLC, we are using a microporous spherical silica particle. So we use a silica gel stationary phase. So that stationary phase, it has got a lot of advantages. However, we sort of derivatize it on the surface, or we coat it with a different compound depending on the separation mode that we are using, right? Okay, so maybe I can just end with that, right? So in GC, we have got a number of stationary phases, polar and apolar. In HPLC, we have got silica stationary phases. So these are the microporous spherical silica particle. So these are actually spherical in nature, and they have got pores. And these have got advantages, you know. Those pores that it has, you know, it actually suits it because it has got high surface area. It is, in other words, there is high capacity or large capacity, you know. So for example, in GC, for example, overloading the column would be like, you know, a nightmare. But for HPLC, overloading wouldn't be much of a nightmare, because these silica porous spherical silica particles have actually a large capacity, you know. And the most important thing about these types of stationary phases, obviously they are stable, you know, at high pressures, you know, because as you take note that in HPLC we use high pressures, right? And in GC, the pressures that we use in GC are quite low compared to HPLC. Remember, in GC we've got an open tubular column. In HPLC we've got a packed column, hence high pressures are a necessity. So the most important thing about these types of stationary phases is that they have got solenoid group in them, you know, and then the hydrogens on the surface of this stationary phase can be replaced or substituted with another functional group. depending on the separation mode that we are using for HPLC. All right, guys, do stay blessed and enjoy the rest of your day. That was just a brief introduction to the differences between GC and HPLC.